Hello, everyone. My name is Benjamin Wong. I'm one of your two ISAs this term for CS 145. In this tutorial 0, I'll be going over some of the core concepts from week 1. So the beginning student language has a lot of great stuff already built into it. We have numbers, positive, negative, real, even, complex. As a little highlight here, we have infinity. This plus inf.0 represents positive infinity, and we also have negative infinity as minus inf.0. Strings in Racket are in double quotes. Symbols are preceded by a tick. Booleans can be represented by the word true or false, number sign true or false, or number sign T or F. Characters are a bonus one, and they are the building blocks of these strings. They're represented in a rather ugly fashion, hashtag, backslash, and then the character itself. Finally, we can combine these data to get some useful programming done. We can get the computer to do the work. We have predicates, number 13. Number determines whether the argument is a number. So this one in Racket will produce true. Boolean goose also produces true because goose itself is not a Boolean value. So Boolean goose produces false. And then this outward expression will evaluate to true because false is a Boolean value. For logic, we have and, or, and not. And will take a bunch of Boolean values and return true if they're all true. Or we'll take a bunch of Boolean values and return true if at least one of them is true. Not will take a Boolean value and give you the opposite of whatever that Boolean value is. We have some other built-ins like the inexact to exact, which doesn't do exactly what you would hope it does maybe, because you will lose precision when converting an inexact number back to an exact number. We have the trigonometric functions and a built-in pi constant that you can use by referencing it as pi, pi, and absolute value. So if is one of the special forms that you'll have to master. And if takes 3 expressions. It's expecting a Boolean and then any 2 other expressions. If the Boolean is true, it'll evaluate this expression. If the Boolean is false, it'll skip over this expression and evaluate this one. So here are some if statements, and we're going to see what they evaluate to in Dr. Racket. So here I am now in Dr. Racket, and I'm going to see what this first one evaluates to. False. So here's the first part. If we evaluate this condition, is 0 less to infinity? Yes, 0 is much less than infinity. So we're going to take this expression, number, string. String isn't a number, so it gives us false. And notice this black highlighting here. The black highlighting means that the code was not run. And we'll see why that's actually really important in a couple examples. So here's another one. If you've programmed before, you may have heard that 1 can be used as true and 0 as false in some cases. In the case of the beginning student language of Racket, this does not apply. The beginning student if is only looking for true or false, is only looking for a Boolean value. Our next one is kind of interesting. The first part is trivial, it's true, so it'll go straight to this expression. So let's see what happens right there. So Racket will spin out the following message, division by 0, really useful. So if true, went to this expression, divide 1 by 0, Racket says, I don't know what to do with that. This last if statement is the exact same, except it's got false instead of true. So it will skip over this and go straight to dividing 0 by 1 and give us 0. So even though there was an error producing code in this if statement that ran, Dr. Racket didn't even run the code, so it didn't even care about that division by 0. Next, we have definitions. And the 2 ways that we have of defining things right now are functions, so define name, and then a bunch of variables, and then an expression. And then also define by name. So this is like your constants. So here's an example of a function, define the distance, and then a definition of a constant, define product to multiply 4 by 4. So this is just a constant of 16, and I'll show you what this distance function does right here. So I'll run my program, and then this is your standard Euclidean distance. So distance between 2 points or 2 vectors in the xy plane. So I can call distance 0, 0 1, 1. And it'll give me the distance of 1, 1 from the origin. So that's just square root of 2. Similarly, I can take the distance between, say, 2, 3, point in the xy plane, and then 3, 2, a different point. That'll give us square root of 2 again. Again, the distance of 4, 4, and 4, 4 should return 0, and it does, luckily. Now, another thing here is recursion. This is a big one. So I'm going to give you a little example of a recursive program, and that is GCDs, or greatest common divisors. So the greatest common divisor of two numbers, x and y, is the biggest number that divides them. And depending on your definition of GCD, biggest can mean a few things. For us, we'll just take absolute value, which is the simplest one and works great for the integers. So here's my GCD file, and I'm gonna just do a quick example up here of finding a GCD between 32 and 50. So for my recursive algorithm, I'll use the Euclidean algorithm, which you'll learn about in your algebra courses, and I won't prove here. I'll just do a proof by example. So the first step I'll do is take 32, and then I'll take the remainder of 50 modulo 32. So that is 50 minus 32 in this case, which is just 18. And then now I'm going to have, in my next step, 18, and I'm going to take 32 modulo 18, which is 14. Finally, I'm going to keep going like this. I'm going to take 14 and then 18 modulo 14, which is just 4. And in my next step, I'm going to have 4 here and then 14 modulo 4, which, if I recall correctly, is just 2. And then finally, we're going to get 2 and 0. And now it's obvious that the GCD of 2 and 0 is just 2, because 2 is the biggest thing in absolute value that divides 2, and everything divides 0. Now, the part of this proof that I have kind of glossed over is that at each of these steps, it preserves the GCD. So with that example in mind, I'm going to write a program, define my GCD of x and y to be if, well, it was really easy when y was 0, when my second value became 0, I could immediately see that I could return x. Now there is the case that you get 2 zeros and everything divides 0, so it won't give you a good GCD, but for reasonable inputs, this will work. And then if y is not 0, I have to do this step where I take the modulo, or the remainder. So I'll call my GCD on y. I'll have to switch the order, or else I'll just keep taking the modulo of the same thing over and over again. And remainder, which you should remember from assignment 1, of x by y. So let's see how this works. Let's see this in practice. So I'll take a GCD of 32 and 50, and it'll give me 2, as I expect. GCD, oh, I don't know if you caught me there, but I typed GCD and not my GCD, which was, my GCD was the function that I just defined, and GCD is Racket's built-in GCD. So I actually cheated there, because this would give me the right answer even if I wrote a bogus program, even if my program did not work at all. So my GCD will compute GCDs as you would expect, but interestingly enough, if I throw in 2 negative numbers, I will get a negative GCD, and Racket's GCD, maybe a bit more competent than my short recursive solution, will give me the absolute value. So really quickly, I'm going to go through steps for evaluating my GCD on 32 and 50. And I'm not going to be super careful about it. I'm just going to go through them quickly so that you can really see that the Euclidean algorithm is what's going on here. So what I did, so function substitution is step 1. Evaluates 50 is not 0, so I don't have my super nice case. I can't use my trivial case. But I'm going to reduce, take the remainder, and basically that first one just swap the order of them so that I can get my smaller one in the second position to take a remainder. But I'm going to do the same thing, see that 32 is not 0, take the remainder, get 18. So you're going to start to see this familiar pattern. 18 is not 0. Take the remainder again, get 14. These numbers that we wrote out in our application, our example of the Euclidean algorithm. And eventually, after taking a few steps, you'll see that this code exactly walks through what we walked through in the Euclidean algorithm. Finally, here are some practice problems to test your week 1 knowledge. If you have any questions at all, Rivers Chen and myself, Benjamin Wong, we're your ISAs. Our whole job this term is to help you find your own success in this course. So I really hope that you reach out to us on Piazza. You can email cs145@uwaterloo.ca to reach either of us. I hope to hear from you, and I hope that you have a great time in this course. Thanks for watching this tutorial video.